Good afternoon, everyone. Today we're going to video on integrating by parts, and we're going to integrate this integral specifically. X squared times sine of 2x dx. So we'll start off by reminding ourselves of our general integration by parts equation. That is, the integral of u times dv is equal to u times v, which is the integral of the dv part, minus the integral of v du. So we're kind of switching things around in a weird way. So we have to start off by figuring which parts of the integral are we going to call u and which parts of the integral are we going to call dv. Now, typically, and as you do, there's no real shortcut around doing a bunch of practice problems to really get an intuitive sense of which parts are typically best suited for what. But when you do get the hang of it, these are often fairly quick. Because, for example, if we look at the first part of the integral, the x squared, I'm going to pick x squared for u, knowing that when we differentiate this, du is going to make the exponent go down. Because differentiating a polynomial always has the exponent going down. And so du is simply 2x dx, which is simpler to integrate and leads us towards simpler and simpler to integrate every time we iterate. To the contrary, that sine of 2x is well enough suited for dv, because integrating a sine function isn't the end of the world, right? It simply becomes a negative cos function. To the contrary, differentiating a sine function also becomes a cos function. So we really don't make our lives much easier by differentiating rather than integrating. But here, our lives do get easier every time we differentiate because the exponent drops down every time. Okay? So if dv is sine of 2x, then v is going to be negative cos of 2x. And reminding ourselves of the chain rule, if we were to differentiate cos of 2x, we would get 2 negative sine 2x, and so let's make up for that with a denominator of 2, okay? So now that we have established our u, dv, du, and v, we can go ahead and write this out, and so we'll have u times v, so that's x squared times negative cos of 2x over 2, minus the integral of v du, so v is negative, we can say negative 1/2, we can pull out a negative 1/2, the integral of cos of 2x, v du, and du is 2x dx. So, well, we can pull the 2 out front here and just write the x inside. So we'll have x cos 2x dx. Okay? We can simplify this a little bit. The 2's here we cancel out nicely. And so what we'll have is, we'll have a negative 1 over 2, or if you'd rather, negative x squared cos of 2x all over 2, subtracting the negative, and so we add, the 2's cancel out, the integral of x cos of 2x dx. Now we're not done, right? Because this integral isn't trivial to evaluate, right? We're gonna have to use another iteration of integration by parts, which is why I chose this example. But it's very similar to our starting point. The only difference is we have cos instead of sine, which works essentially in the same manner, but notice that the exponent on the x has dropped down by 1. If we drop it 1 more time, reminding ourselves that this is an exponent of 1, it's going to completely disappear. And so one more iteration of what we just did ought to take care of that. Okay, so this term we can't forget about, so we'll have negative x squared cos of 2x all over 2 plus, and now this new integral, we're going to apply the same technique. So let's pick a new u and a new dv, like so. I'm going to opt for a similar idea as at the start. So I'm going to pick x to be my u, because knowing that when we differentiate our x, the derivative of x is just 1, and so all we're going to get is 1 dx, or if you'd rather, just dx. Okay, so that'll be essentially gone, and our dv will be cos of 2x dx. Sorry, I should have added that in there. Let's be proper and not lazy. So easy to make a mistake like that. Now, if dv is cos of 2x dx, then the integral of cos is sine. And so we get our sine of 2x, but reminding ourselves that we would use the chain rule if we were to differentiate this. So if we were to differentiate sine of 2x, we would get 2 cos 2x. And so to make up for that, if we divide by 2. Okay, factor of 1/2. And so now we can apply the same technique that we applied at this moment in time down here. And so we'll have this integral will be u times v, so that means u times v, so that's x times sine of 2x all over 2 minus the integral of v du, so that's v du. V is sine 2x over 2. I'm going to pull the factor of 1/2 up front, and we'll have the integral. Du is simply dx, so that's going to be easy to deal with. And the rest of the v, the 1/2 is already up front, so we can ignore the denominator. And so all we have left in our integral is sine of 2x, okay? And that we do know how to integrate, right? So now, let's not forget about our first two terms. We have negative x squared cos of 2x all over 2 plus x sine of 2x, again, all over 2. And then the integral of sine of 2x, we've already done that, to be honest, is going to be negative cos of 2x over 2, remembering the chain rule. And so we'll have subtracting a negative once we integrate, so we'll add, and we'll get another factor of 1/2 combined with the 1/2 that is already in front of our integral. We'll get 1/4 cos of 2x, and then since we're evaluating an indefinite integral, we always add our constant c at the end. And then we could clean this up a little bit. If we wanted to get a common denominator, we could multiply all of this by 2 over 2, and multiply this by 2 over 2, since we have the denominator 4 here. And so we could write all of this as 1/4 times, this is a negative term, so let's write it as, let's say, cos of 2x plus 2x over 2 sine of 2x, and then minus 2x squared cos of 2x, and then 1/4 is multiplying all of this, so let's finish off the big brackets, and then always our constant c at the end. Adding c is such an easy thing to forget, but you will lose marks on an assessment if you do. And so there we are, okay? An integration by parts problem where there are 2 iterations of how to use this technique. I hope this kind of helps with your understanding of what elements of an integral are best suited for u and dv accordingly, respectively, I mean. And again, the more you do practice problems, the more you'll get a sense of which parts of the integral are best suited for what. Eventually you'll get super efficient, and these won't be as daunting as they might look at the start. This is the last technique that is often taught in Calculus 12. Oftentimes at first the trickier looking technique, but once you get the hang of it, you know, your life, honestly, you know, there's no one part in this solution that is inherently awful. It's just a lot of parts to keep together and make sure we don't make any silly mistakes along the way. But, you know, you will get more comfortable the more you practice, and you'll get more efficient, and all will be well. So I hope this helps. If you have any questions, comments, suggestions, please let me know. Thank you so much for watching, and have a great day.